We have a section called Story Problems in 9.4, so we're going to take what we've learned in 9.1 through 3 and do a few application problems, a few story problems. And so the math part won't be new in this section, but organizing our work and looking at a multiple step problem will involve a little bit of work as well. So let's take a look at some of the keys to story and word problems in geometry, at least what I think are some of the keys. What I wrote down is that, number one, you should read through the problem once at normal reading speed, then read through the problem a second time, or more if you need to, underlining the final question and highlighting or circling important numbers or facts. Second thing is to draw a picture. Especially in geometry, we need to draw a picture. It helps us visualize what's going on. And 3, organize your thoughts in space for work. Think about questions like, is it a multiple step question? What do I need to find first? What formulas are required? And other things that you might think about, but those are just a few ideas. So here's the problem. Mr. Swiggum, myself, loves to play golf. He loves it so much that he named his new driver Swagman and doesn't go anywhere without it. He even protects it with an Angry Birds head cover, pictured below. During spring break, he's traveling to Florida and would like to ship Swagman using FedEx. He searched his garage and found a box with the following dimensions: 25 inches by 30 inches by 20 inches tall. Swagman is 45 inches long. Does it fit inside the box? If not, give the dimensions of a box that would work. Show your work. So you can see I just read through that problem once at normal speed. Now I'm going to read through it a second time, and let's take a look at highlighting some of the important parts. Most of the first 3 sentences or so sets up the problem, but mathematically, it's not critical. The critical mathematical part starts at about right here. In that sentence, he searched his garage and found a box with the following dimensions. And this is the important mathematical part: 25 inches by 30 inches by 20 inches tall. Swagman is 45 inches long. All right, so those are the important mathematical parts. Now the question is, which I'm going to underline, does it fit inside the box? So we'll kind of annotate this a little bit. And if not, give the dimensions of a box that will work. And as always, show your work. So even though it's a longer word problem, we need to just think about what are the most important mathematical facts here. And when I read through it a second time, I'm going to highlight those things, underline questions, so we can really focus in what I need to figure out. All right, the other part that I probably should have underlined, well, it says that I found a box. So gives us the dimensions 25 inches by 30 inches by 20 inches tall. So let's think about what we need to do here. First, maybe we can draw a picture. Now it's a rectangular box, and so when you're drawing a rectangular box, and I am no artist by any stretch of the imagination, but drawing a 3-dimensional box is sort of an important thing to be able to do because that shape is something that we see quite a bit. So draw a rectangle, and then draw another rectangle that is congruent to the first one, just a little bit offset. And what we're going to do is I'm going to make a little dotted line, because this line is actually going to be hidden here, and it's going to give us a little bit of that depth perception. And then I'm going to go straight across with another dotted line. And I want my rectangles to be about the same size, so I'm just going to have to eyeball it. And then we'll draw up again and over. So I've now created 2 rectangles that are hopefully pretty close to congruent. I'm just sketching it. And now I'm just going to connect the corners together of these 2 rectangles that correspond. So the upper left corners we're going to connect together, the lower left corners, and I'm actually going to make that one dotted for the depth perception part of it since it's a hidden edge. Top right corners, bottom right corners. Okay, so now I have a rectangular prism. I've got a picture of what's going on a little bit here. Now I'm going to label. We've got, say, 30 inches by 25 inches by 20 inches tall. And what I want you to think about, or what we need to think about, is that if I'm going to ship a golf club in here, I'm going to have to think about what's the longest part of this box. And the longest part of this box is not necessarily laying the club right on the bottom. It actually, the longest part of the box is going to diagonal from the back top to the front bottom and diagonaling across the box. So if I call this A and this B right here, this segment right here is what's going to be the longest dimension in my box. So it diagonals kind of across the box, front to back, top to bottom. So that's really what I'm going to be looking for right there, is that dimension. And I could have drawn that same dimension from here to here, and from here to here. So there's a few different places I could draw that, but let's just take a look at this. Now, that dimension right there is going to be a part of this little rectangle, or not rectangle, this triangle right here. So I'm going to actually sketch in this triangle right here, because this is a right triangle. And so what I really want is this dimension here, I'll call it X, but that triangle, which I can sketch out on the side, I only know the 20-inch part of it. I don't actually know this bottom distance here, and I certainly don't know X, because that's what I'm trying to find. So I have issues there because I only know one of the side lengths. However, notice that this segment on the bottom here is the hypotenuse of a triangle that goes something like this right here. So it's the hypotenuse of this triangle. So what I'm actually going to do is start there, because this is a little right angle down here. To start there, I'm going to calculate the length, and maybe I'll call it something like y. I'm going to calculate y right there, and that way I'll get the bottom of my red triangle, my bottom leg here, and I should be able to use the Pythagorean theorem. So you can see how I'm kind of sketching this out. I'm talking this through in my mind, and even though I'm teaching this right now, this is something that you should do, especially on these word problems, before you really dive into the math part. Try to get it straight in your brain first. It will be helpful. It's going to be a little extra time, but hopefully it will pay off. So first I'm going to find y. So first, actually I'm going to use a different color. It's easier to see here. So first find y. And y is going to be the hypotenuse of this triangle right here that's along the bottom, this green triangle right here, that is 25 inches and 30 inches, and then y is the hypotenuse. All right, so now let's do the Pythagorean theorem. I have got 25 squared plus 30 squared is equal to y squared. 625 plus 900 is equal to y squared. That means I've got 1,525 is equal to y squared. And therefore, y is the square root of 1,525. All right, so now I know that that length, that y length, that hypotenuse of the bottom of my box is equal to the square root of 1,525. Now, I could get that decimal. I could, but I'm not going to yet because I'm not really interested in that decimal. I'd have to round it, and I want to keep my answer exact in my problem as long as I can. So now I'm going to actually go to my second triangle, the one that I've sketched out in red here in my box, that's going to have x. And now I want to find x. And x is the hypotenuse of that red triangle, and I know that red triangle has a side dimension of 20 inches. And now I found that bottom dimension of the square root of 1,525. So the bottom dimension of that red triangle is the square root of 1,525. And x is what I'm trying to find. All right, so now let's do the Pythagorean theorem again. So 20 squared plus the square root of 1,525 squared is equal to x squared. 400 plus 1,525. So remember, if I square a square root, the square root of 1,525 squared is just 1,525. So it gets rid of the square root, basically. And so that's 1,925 is equal to x squared. And x is the square root of 1,925. Now let's see what decimal that is. If we punch that into our calculators, we get right around 43.9 inches. Okay, is that long enough to fit Swagman? Remember Swagman over here, there he is 45 inches long. So no, that's not enough room in my box. 43.9 inches is not enough room. Swagman will not fit. Oh, bummer. I'm going to have to find a different box. Okay, but the rest of the question was, what dimensions would work? Well, I could do a number of things to try to figure out what dimensions would actually work here. I could change the 30 inches, the 25 inches, the 20 inches. So there's a number of possibilities here. Now, what I figured out was that Swagman would fit if the height was changed to, I'm going to write and talk at the same time. If the height was changed to 23 inches. All right, so if the height was changed to 23 inches, then it would work. So let's actually draw this out. So if I've got 23 now instead of the 20, and I've got the square root of 1,525 is that side, I'm just going to now show that this does work. So 23 squared plus the square root of 1,525 squared is equal to x squared. That would be 529 plus 1,525. 1,525 is equal to x squared. 2,054 is equal to x squared. So x is the square root of 2,054, which is about 45.3 inches. Okay, so 45.3 inches should fit Swagman. Swagman's 45 inches. It's going to be tight, but mathematically, that looks like that's going to work. And so you can see how we mapped out our problem, we talked through it, we made a sketch, and we organized our work, and hopefully you will do the same when you have a story or word problem.